Hey everybody, we're going to do, as you can see, an example here that turns out to be integration by parts with a natural log. And then there's actually a little problem with this. I've used this problem on assignments before, and there's something I noticed about it this time that was actually a mistake that I will correct moving forward. But we'll get to that at the end. There's a few interesting things that show up in this problem. So let's first just approach it in the most, I think, straightforward way, and then discuss where a little problem arises. And I want to do a little bit of pre-work. We've got a natural log. We're going to have to do an antiderivative natural log at somewhere in this. So I'm going to remind myself by computing the antiderivative of the natural log of x. And this is a problem that we can do with parts. If I let u equal ln of x, du is 1 over x dx. dv is equal to dx, and v is equal to x. Following integration by parts, we get x natural log of x minus 1 over x times x dx, which of course becomes, I didn't leave myself enough space. Here, we'll do it here. We get x natural log of x minus 1 dx, which then becomes x natural log of x minus x. So here's our antiderivative. We'll be using that at some point. It's a good one to have. You can check this result by taking the derivative, but I'm just going to keep it here as something we're going to use down the road a little bit. Okay, so we'll keep that off to the side. But before we can do that, we can't apply this rule because we have more than natural log of x going on, right? We've got a lot going on in there. And we need to deal with that first. And so here's a good example of if you approach this problem and haven't seen something like this before, you don't have a lot of options. You can try a substitution, but nothing's really going to work. But the argument of natural log, that polynomial in there, that quadratic in there, offers some options, right? And again, even if we don't know where this is going, it might occur to us, I'll do this off to the side, that we often factor quadratics. And this one that we have here can be factored as x plus 4, x plus 9, okay? So I'm repeating myself, but I think it's an important thing to repeat. I don't have to know at this point whether or not this is going to help. All I know is I don't know what else to do, so I'm going to try it. So I have the natural log of x plus 4 times x plus 9, right? In other words, it is perfectly clear that these are equivalent expressions, that I am allowed to substitute this quadratic with those two factors, okay? Now I'm looking at a natural log, and it's got these two factors, and I'm going to try a natural log property. Again, I'm just using something I know to be true and seeing if something nice comes out of it. We have this rule of natural logs. Natural log of A plus natural log of B, okay? So applying that, oops, skipping steps that I don't want to skip. We can rewrite this as, right? It's like we're saying x plus 4. This is like the A. This is like the B in that rule, okay? So we split that natural log up, and now we can use rules of antiderivatives or indefinite integrals to write this as two different integrals. And let me note here, I have made a small mistake, and we will come back to it. So if you've noticed that mistake, don't worry, we will get back to it. But it's a pretty technical and small mistake that I anticipate most of us have probably missed. And for the time being, I'm not going to worry about it. So now, how do we deal with these two integrals? Well, I'm going to use substitution on both of them. The first one, I'm going to substitute t is equal to x plus 4, so that dt equals dx. And on this one, I'll do s equals x plus 9, so ds equals dx. Whoops, there we go. And so now our integrals look like the natural log of t dt plus the natural log, antiderivative natural log of s ds. I can apply this rule that we computed in the beginning, or maybe already had memorized. And so I get t natural log of t, right? I can apply this rule because now I have exactly the same thing. Changing the name of a variable doesn't change the meaning of the rule. I can think of this rule as the antiderivative of the natural log of an unknown with respect to that unknown, right? Which is really clumsy. We just say x, but this is just another variable, minus t plus s natural log of s minus s plus c. And then I substitute in what these are equal to. Let me scroll down just a little bit. Okay, so this becomes x plus 4 natural log of x plus 4 minus x plus 4, and then plus x plus 9 natural log of x plus 9 minus x plus 9 plus c. And if we want, we can do a little bit of cleaning up. I'm going to do this, x plus 9 natural log of x plus 9, and I'll have minus x, so I have minus 2x, and then I have plus c, and I've also got a minus 13, okay? So here's one little point of confusion. We've got this arbitrary constant c, right? Remember the meaning of c. It's an arbitrary constant saying that if you start with this antiderivative I have here, the x plus 4 natural logs, all that, minus 2x, that's like our base. And then adding any constant to that, or subtracting a constant, or adding a negative constant, still has the same derivative. So they're all, it's a family of antiderivatives. So if c is some arbitrary number, c minus 13 is also an arbitrary number. In other words, that minus 13 isn't really doing anything important for us. It's just the family is this natural log and x plus 4 thing with minus 2x plus any number. I don't need plus any number minus 13. If it's going to be plus 100, I could make c 113, and then minus 13 makes it 100. Or I can just write it as plus some number. The minus 13 doesn't change the fact that this is, we can have any constant there at the end. And so we often will write it without that constant when we can. You're almost always safe to do this. We will see some problems later on in the course where we need to track a little bit. You sometimes end up with more than one constant, and even if you don't know what they are, they might have some relationship to each other. Like one of them, they're both arbitrary. They're arbitrary, but one of them is always double the other one or something like that. And then you do have to kind of keep track a little bit. But in this case, there's no benefit to adding that minus 13 there. Okay, so a few things. There are many ways to write what we have here. And so I know that there are different methods for computing this. And you might get something different. And so, for instance, let's look at a graph. Let me zoom out for a minute. I have a graph somewhere on this page. There it is. Let's pull it. Whoops. I do this. There we go. All right, let me make it a bit smaller. Oops. There's always something strange about how it handles these graphs. Okay, so let's put it up here and zoom in a little bit. Okay, so here's our graph. In fact, I'll move it a little bit closer. Okay, here's our graph. So a couple of things. Here's the graph of the function. I have of the function that we came up with. One thing you can do if you find that your results looks different than mine, if you went about this in a slightly different way, and there are some other ways to do it, you can graph them. So here's an alternative answer that somebody, oh, that's my answer. You can see that this answer up above, the red graph, is different than ours. It's got it written out in a little different way. And there's just a little bit of algebra getting there. And you can graph and see that they're the same thing. Sometimes people will do a graph, or you'll see your graph is something shifted. If somebody has a slightly different answer, it might be shifted, but that again is okay because that's our arbitrary constant, and those kinds of differences don't really matter in terms of antiderivatives. But more importantly, I want to consider something. We have our graph only exists in this case from -4 and greater, okay? And so that implies something about this original function, right? That it only has an antiderivative for -4 and greater. The question is that true? And it turns out it's not. We made a mistake. So let's first look at the original function. Here's the original function. We can see that it has something funny going on at -4 and also at -9, but it exists below -9. Okay. Well, here's the problem. Well, first of all, let's look at why this is. Here's the quadratic that's inside the natural log. Natural log, remember, only exists for positive numbers. And you can see between -4 and -9, x values there, they give us 0 at those 2 points. Those are the roots of that quadratic, and it's negative in between there, so the natural log can't exist. So we see an asymptote as it approaches those 2 roots. Let me use fewer pronouns. We see an asymptote for the natural log function as its argument approaches 0, right? So as the quadratic inside approaches -4 and -9, from -4 from above and -9 from below, the inputs to natural log are approaching 0, and natural log spits out numbers that are larger and larger, but in the negative direction, right? So think back to your natural log graph, okay? So that's why this looks this way. Well, we obviously, looking at this, if this right half of the function, right, this part of the graph has an antiderivative, it seems reasonable to think that this left half should, right? It's a very similar looking graph, and there's nothing sort of extraordinary about it relative to the other that would suggest that it shouldn't behave in a similar way, or it shouldn't have an antiderivative. So what mistake did we make? Well, it turns out that the mistake we made was right here, between these 2 steps. When we went from the natural log of x plus 4 times x plus 9, so this is all in the natural log, and I decided to rewrite this as, this is not always true, and this is an easy thing to miss. I missed it. This is only true, in other words, let me write it as in a simpler way. This is only true when A and B are both greater than 0, right? Why is this the fact? Well, look what happens. When we had them multiplied together, when both of them are negative, so again, when x plus 4 and x plus 9 are both negative, when is that? Well, that's when x is less than -9. So if x is less than -9, both of these are negative, right? If it's between -4 and -9, this one's negative, this one's positive, natural log doesn't exist. If they're larger than -4, if x is larger than -4, both of them are positive, and the argument of natural log is positive and exists. But if both of them are negative, when x is less than -9, then we get x plus 4 is less than 0, and x plus 9 is less than 0, which means x plus 4 times x plus 9 is greater than 0. Okay? Which means we can put this into the natural log. However, when I split them apart, now they're both negative, and this is not defined, and this is not defined when x plus 4 and x plus 9 are both negative. And so by splitting them apart, I implicitly assumed they were both positive, which is why my result only showed up for the place where they're both positive. We missed a portion of the graph. And so using a more complicated solution, you actually get an antiderivative with this graph that shows that exists on both above -4 and below -9. Now, the methods for getting that are quite complicated. And so instead of expecting people to do that, I've changed this problem to say for x greater than -4, because this is actually the point of it, was this kind of solution, and I didn't catch that error when I found this problem and wrote it up the first time. Okay, that's it for this one. There's a lot of good stuff in this. I think most of us tend to need a reminder about properties of logarithms, as well as being able to factor quadratics and recognizing quadratics and that they're easily factorable. And then of course there's some good calculus in here with these antiderivatives. Okay, that's it for this one. Thanks everybody. I will see you next time.